So we are going to wrap up this section 3.4 here today, which has been on a number of things, finding derivatives of log functions using a process called logarithmic differentiation to take derivatives like the one you see above, functions of x raised to the function of x. Got a couple other odds and ends basically to wrap up this section. The first one is once again the power rule. Never get tired of that. So essentially we've phased this in terms of what we were able to prove at the time. And so the last phase was we've already proven it all the way up through integers, then negative integers, then rational exponents, and now we can show it for all real numbers if we use logarithmic differentiation. So if I start off and I say, okay, let's suppose that y is equal to x to the n, where n is now any real number. So where n is any real number, well, what we're going to do is take the natural log of both sides. So we're going to take the natural log of the left and the natural log of the right. And so when we do that, we're going to have natural log of y is equal to the natural log of x to the n. So now on the right hand side we can apply our property of logs and bring down that real number n as a multiple times the natural log of x, and that will then mean when I take the derivative of both sides with respect to x that I will actually not even need product rule on the right hand side, because n is just a real number and that's going to get carried along as I take the derivative. So this will be easier than our last logarithmic differentiations were. So derivative of natural log of y will be 1 over y dy dx. N gets carried along as a constant multiple. Derivative of natural log of x is just 1 over x. And so my last step here, we're going to just multiply both sides by y, and we are now going to have that our dy dx is going to equal, oops, I forgot to show the y on the right hand side here, multiplying both sides by y. So we are now going to have our n times the 1 over x, and then the y gets replaced with what it was originally, which was x to the n. And then with our rules of exponents, x to the n divided by x to the first is x to the n minus 1. And so there we finally have proven the power rule for any real number. So what does that allow us to do? Probably what you would have done anyway, even if we hadn't proved it yet, which is if I now have something other than just rational exponents. I could have something like x to the pi, an irrational number, but a real number. I could have plus 2 over, let's say, x to the e power. So if I was going to take this derivative, probably the first thing I would do would be to rewrite this in that second term anyway. I would probably bring that up as my 2x to the negative e, and then we can take our derivative. So just power rule. So we bring down the pi, and then x to the subtract 1, pi minus 1. We bring down the minus e, so minus 2e, x to the negative e minus 1. Okay, so just power rule, but now with any real numbers. An exponent is now proven. All right, last little topic in this section, we have a couple of limit definitions of e, which have been mentioned before. And so why does this get thrown in this section? Well, we can use the derivative of the natural log function to actually give some sort of a justification for why these limits have to be the definition of e. So we're going to take a look at one of them, and then we'll look at a homework type of question, probably involving the other form. So we'll do a little bit of something with both of those. All right, so let's take a look at this second one. So first what we're going to start off with is we're going to say, okay, let's let f of x here equal natural log of x. So we've been working a lot with natural log of x. Now, it's certainly true then that, okay, this then tells me it's certainly true that f prime of x is going to be 1 over x. And that would certainly imply that f prime of 1 would equal 1 over 1. So f prime of 1 is obviously equal to 1. Okay, well, what else could I say? Okay, the other thing I know, so let's also kind of just, so also, what should I say? We'll just say it's true that if I take the derivative f prime, I could do it with my limit definition. So I could say that would equal my limit as h goes to 0 of f of x plus h. Let's go right to thinking of that as natural log of x plus h. I'm sorry if you hear my dog barking in the background. Natural log of x plus h minus natural log of x all divided by h. Okay, so what does that tell me would be true then about f prime at 1? So f prime, let's continue that down here, at 1, hold on, so I'll just say is equal to, I'll put an arrow I guess here, so let's rewrite that. All right, f prime of 1, so subbing 1 in for x. So what would that tell me? This would equal the limit as h goes to 0, natural log of 1 plus h minus natural log of 1 all over h. And natural log of 1 we know to be 0. So this now tells me that f prime of 1 is equal to the limit as h goes to 0 of natural log of 1 plus h all over h. So here is something that I know. These two are both representations for f prime at, that's awfully dark. These are both representations for f prime at 1. Okay, so let's take a little bit lighter of a highlight here. Okay, so this is now hardly even visible. So this is going to have to equal this. So these are both representations here for f prime of 1. So these two are going to have to be equal to each other. All right, so I'll just say, so the limit as h goes to 0 of natural log of 1 plus h over h has to equal 1. Okay, so let's think about how I can rewrite this limit here. If I think of divided by h as multiplying by 1 over h, and then if I'm multiplying by something, that means I can take this 1 over h and I can, as a property of logs, move it up as an exponent in that log expression. And so I now have, so this is now going to tell me, so continuing here, that my limit as, it's supposed to be an h here, rewrite that, my limit as h goes to 0 of natural log of 1 plus h raised to the 1 over h, that is equal to 1. Well, when we have a nice continuous function like the natural log, we have a property of limits, which essentially is going to let us bring the limit inside of that log. I mean, that's where the 1 over h, that's where the h's are, right? So it's kind of your instinct allows you to do this, and that is correct. All right. So I now have natural log of something is equal to 1. So if I have natural log of something, so here's this natural log of, change that to this, okay. So natural log of something is equal to 1. Well, what do you know that has to be? Natural log of what is equal to 1? E. So this implies, so this is going to tell me, so this implies that the limit as h goes to 0 of 1 plus h raised to the 1 over h, this, oops, has to equal e, sorry. So we know that this quantity, this has to equal e, because we know that the natural log of e is what's equal to 1. And so that is how we get to that final, oops, oh, I just dropped my pencil. That's how we get to that. All right, so that is the second form that you see up above. Okay, so you have two different forms for the definition of E. If you start to look at them, you can see their parallel relationship. Like if you take h to 0, in the right-hand side, my dog, I'm so sorry. So if we have h going to 0, and then you look in the left one, limit as n goes to infinity of 1 over n, that 1 over n is going to 0, and then the right one, the h is going to 0. So if you kind of compare these, like as n goes to infinity, 1 over n is going to be going to 0. And so here as h is going to 0, this is going to 0. So you start to see the relationship, and then the same thing with that exponent power. Here n is going to infinity, and then over here, as h goes to 0, 1 over h is kind of going to infinity. So we have a parallel sort of situation here that we can just kind of casually observe. And then let's just take a look at one example here, something that you might see in your notes that might involve one of these definitions. So it might just be something as simple as express the limit as n goes to infinity of 1 plus 1 over n raised to the 9n. We're going to express that in terms of E. And so this is obviously very similar as we kind of look at this. This looks a whole lot like that first form of our limit definition of E. So as we look at this, what we see here is that we are going to apply a property that says, first, just I guess a basic exponent property. So what we know is powers to powers you multiply. So let's just start with that. So 1 plus 1 over n raised to the 9n, I could raise that to the n and then raise that whole quantity to the 9th, because powers to powers you multiply. And then we have a property of limits that says essentially the power of a limit is the limit of the power. You can kind of bring that limit on the inside of that. And so we're really focusing then on what's the limit as n goes to infinity of 1 plus 1 over n raised to the nth power, and then taking that result to the 9th. And so that, of course, is our first definition listed up above of E. And so that's what this is. And then we still have, obviously, this outer power then here raised to the 9th. Okay, so that is, of course, our final answer, expressing that in terms of E. All right, so that's the end of this section. And when we come back next time, we're going to start to look at, we have quite a few topics in 3.5, differentials, linearizations, linear approximations, and something called Newton's method. So we'll be finishing up this last section in chapter 3, starting in the next video.